Okay, well, thank you. I'd like to thank the organizers for inviting me. It's a pleasure to be here. So let me start with a little motivation. So here, let's take y to be a smooth del Pezzo surface. In other words, minus ky is ample. And then it's known that del Pezzo surfaces of degree d, which is the degree of minus ky squared, is really more or less the same thing as root systems of rank, well, 9 minus d and type E, more specifically E9 minus d, well, where you have E8, E7, E6, and then by convention E5 is D5, E4 is E4, and E3 is A1 plus A2, and then you stop there. You don't try and go any lower. And what is the connection? Well, there are certainly many explanations for this connection. But the point I want to make here is that if you look at the projective geometry of y, you can think of that more or less as the ample cone of y. And there you don't really see the connection very concretely. Instead, when you look at the ample cone, here the walls are the exceptional curves. And a priori, they don't seem to have too much to do with a root system. So where does the root system come in? And there's sort of two explanations. One explanation is the explanation of Duval, which is you can make y singular. And if you make it as singular as possible, you get a Dinkin diagram of rational curves. Of type E9 minus d. But the other explanation, which was in some sense more classical, is the following, that the root system, or at least the Weil group, is a group of symmetries. In fact, it's really the group of symmetries of the ample cone. Okay, and this picture goes back a long way. And this is what I want to talk about generalizing in some sense. Before I do, let me just make a remark. Again, this is kind of special del Pezzo surfaces. First of all, what are the exceptional curves on a del Pezzo surface? That's really the same thing as cohomology classes, which are square minus 1, and such that alpha dot ky is equal to minus 1. And I guess I should have said here, but I should say once and for all, I'm going to work over C. Although, in fact, probably more or less everything generalizes. And then also, what about the minus 2 curves? Well, again, pretty much there's no real restriction. If you have beta a class in H2 of YZ and a beta dot, so this just means associated cohomology class is equal to 0, then there's some deformation of Y such that beta becomes the class of a curve C, where C is isomorphic to P1, and therefore C squared is equal to minus 2. Okay? So, sorry? Sorry. Right. Right. So I should put that in. Okay. So, so I'd like to generalize this to more rational surfaces, and in general, it's hard to say much about a general rational surface. So the natural assumption to make is y is going to be a smooth rational surface. And I want minus ky to be effective. So in D, in fact, I'm going to look at pairs y comma d, where I pick a smooth rational surface and I take a section from minus k. And in addition, I want to assume D is reduced. Again, that's a sort of fairly reasonable geometric assumption. And then there are only three possibilities. First of all, D is a smooth elliptic curve. Secondly, D is a cycle of smooth rational curves. Meaning transversely, with a possibility the cycle has length 1, and then it's nodal. Or this is a so-called triangle case, which is that D looks like a reduced Kodaira fiber which doesn't have normal crossings. And I'll draw the picture, but these are sort of exceptional. And there are only three of them. Okay, so in the first and the third case, the supply is not that plentiful. It's really in case 2 that we get a large supply. So the assumption throughout now will be that we're in case 2, that D is a section of minus k and D is a cycle of smooth rational curves. Although certainly many of the things I say will apply to the other cases as well. Okay, so we assume in case 2. And then in general, so I'm going to let D equal d1 plus dr. So r, if I have to give it a name, is the length. And we also have the self-intersection sequence. Self-intersection. D1 up to dr, where little di is just the self-intersection of capital Di. Okay? And it's clear that there's no, well, I mean, I'll say it more in more detail in a minute, but there's no bound both on r, and these numbers in general can be as negative as you like. Okay? So in that sense, this is really the abundant case. Okay? So you could ask, well, I mean, why do we study them? So, reasons to study such pairs. Well, there are sort of two related reasons. One is that they arise in generations of K3 surfaces. You look at degenerations of K3 surfaces, one of the standard patterns is to unions of rational surfaces meeting along cycles of rational curves. Okay? So that's a really nice thing to understand. Also, in terms of cusp singularities, these are a kind of normal surface singularity whose resolution will be one of these where the intersection matrix is negative definite. So these arise very naturally in the study. And the third, let me just sort of toss out a third, which is as follows. For example, if D is contractible, in other words, the self-intersection matrix is negative definite, then you can contract it, and you get a normal complex surface with trivial dualizing sheaf, so say y bar. And so it's an analog of a K3 surface. But you get many, many of them because you get infinitely many possibilities for R and for the self-intersection sequence. Okay? each component will be a smooth rational surface, well, in the so-called type 3 case. And the double curves marked on any component will be a cycle of rational curves. Okay, so the degeneration is built up out of these as building blocks. Anyway, to go back to this picture, in case the cycle is negative definite, you contract it, you get something which looks like a K3. So Y bar is a singular analog K3. Of course, you could say that so is a pair Y comma D is a log Calabi-Yau surface. But either way, you get sort of infinitely many deformation types, and they're all related by by rational operations, and sometimes by smoothings. I'll give some examples of that in a minute. So you can think that this picture is sort of a toy model of the so-called Clemens-Reed fantasy. Whereby if you look at all smooth Calabi-Yau threefolds, for example, that somehow they're related. Now, it's not really clear that this is going to give you much insight into that because the questions here tend to be kind of elementary. But still, it might offer some interesting analogies. Okay, so the next thing I want to say is sort of how are they related? And in general, if you're given a pair Y comma D, what are the birational operations you can perform on it? Well, one thing you can do is pick up smooth point. Sure.
So most of those fractions would not be smooth.
No. I mean, it will be, well, it turns out if the cusp is smoothable, then you can globalize the deformation and get a K3 surface. So in that sense, many of them will and many of them won't. But it's just entirely a local question about the smoothability of the cusp. If I pick a smooth point of D, then I can blow it up, which I'll call an interior blow up. So just blowing up this point, you get some new anticanonical cycle where the self-intersection has gone down by 1. And the opposite operation is an interior blow down. And in general, an exceptional curve meeting D at a smooth point will be an interior exceptional curve. Okay. And the other thing you can do is you can blow up a singular point, okay, and then you get a new exceptional curve here. This has self-intersection -1, and the self-intersection of both of these has gone down. So I'll call this a corner blow up or blow down. Then all pairs YD arise via these two operations from a short list of minimal pairs, meaning that Y is P2 or Fn, where I might as well assume that n is not equal to 1, and you can just enumerate them. And in particular, it's easy to, as a corollary, given any y comma d, there exists a sequence so you make a sequence of here, these are allowed to be, the ones on the coming down this way are allowed to be corner blow-ups or blowdowns, but the ones on the right are only allowed to be interior blowdowns or the identity. So you're never allowed to introduce a new interior exceptional curve, but you may introduce a corner exceptional curve, but in the end you can start here and get to, say, F0 and the standard anticanonical cycle, which is a union of two fibers going this way and two fibers going this way. Okay? So in particular, starting with anything, you can get to this thing, and that says they're all related. One other remark. That comes, I didn't really give you the list, the short list, but I can sort of leave that as an exercise. If we fix the self-intersection sequence d1 up to dr, then there are only finitely many deformation types pairs y comma d with this self-intersection sequence. There may be more than one. It's not too hard to find examples where there are more than one, but there are only finitely many. And the main point is, for any given n, there's a small list of what are possible, and from the di, you just have to bound in. Okay. Those are at least some birational operations that link the families. Then you can ask about smoothings. And you can imagine this in sort of two different ways. One way is you could look at the deformation theory of y. And here I keep the cycle, but I really think of it as a cycle. In other words, I keep the singularities local normal crossings. And this is governed by what's written in various ways as t sub y of minus log d, or theta sub y of minus log d, which is the dual of the one forms with logarithmic poles. Okay. And it's easy to see that this is unobstructed. But another thing you could do is you could consider the deformation theory, but just think of D as a Cartier divisor. So if we look at, so write it this way. So I want to keep this as a Cartier divisor. But not really care about the singularities. This is governed by the complex in the sense that the first hypercohomology is the Zariski tangent space, and the second is the obstruction space. So again, this is unobstructed. And moreover, if you look at the map of functors, where I look at deformations of the pair and then look and record what's happening to D, this is smooth. So what that means is you can deform the pair y comma d here just as a Cartier divisor and arbitrarily smooth the double points. Okay, and in a slightly different but equivalent form, this is an old result of Karras, Laufer, and Wall. I should emphasize that all of these deformations occur in the context of a smooth, y remains smooth under this. There are other deformation problems where you allow y to be singular to start with, and you produce some more exotic deformations. Okay, so those are sort of at least some of the smoothings that, that relate some of these families. For example, you could smooth y until it was irreducible with one node, or even make it elliptic. And the last sort of general ingredient that I want to talk about is the period map. Here, let me let lambda, which if I want to record y and d, I'll write as lambda of y and d. It should be the orthogonal complement of the classes of d1 up to dr inside of yd, inside of h2 of y. And given d, it's Jacobian of degree 0, so, well, let's see, pick not. That's just a C star GM, and the isomorphism is specified by an orientation of the cycle. So if there are more than two components, you just literally orient the cycle. Otherwise, you have to orient h1 of d or say something equivalent. So from now on, I want to assume, given an orientation, and keep that as part of the information. And then the period map in this context is just given v sub y from lambda to gm. Well, you start out with a class alpha and lambda that corresponds to some line bundle, but it has a property that L alpha restricted to di is has degree 0. So L alpha restricted to d is in pick not of d, and you chose a fixed isomorphism of that with g. Okay, so that's the period map. Well, I should say this is a period homomorphism. And the period map, so I'm going to call this phi sub y. The period map sends a pair y comma d to phi sub y, which is in hom of lambda gm. Okay? And I call it the period map because this is essentially the mixed Hodge structure on the surface y minus d. So in that sense, it really is a period map. Then what can you say about it? Well, as I learned always, you should compute its differential. So first of all, the differential is an isomorphism. So the period map is locally biholomorphic. Second of all, it's easy to check that the period map is surjective. Unlike the case of K3s, this is an elementary argument. In a sense that I won't try to write down too precisely, but you can write down a family of deformations. So given a homomorphism from lambda to GM, you can write down a family of deformations where you can assume, say, the monodromy is trivial to be able to identify the fibers, and you can assume that you get any given homomorphism. And then there's a sort of more refined Torelli theorem, which I won't try to state here, which is due to gross hacking. Okay. So now I want to talk about the analog of -1 curves, or what can you really say in general about -1 curves and -2 curves? So first of all, the ample cone. And this is really ultimately going to be the story of -1 curves. Let's say interior.
So can I ask a really wild question?
Sure.
So do you have crystal lines in this?
Not that.
No?
I mean, well, I'm not sure what the analog would be. But maybe there is one. But I don't. So first of all, let me use the following notation. So A of y bar, so this is going to be the positive cone of h2 of y with real coefficients, or rather the component containing ample divisors. And A of y bar is going to be the closure, but only in C plus of the ample cone. Okay, so it's not closed in H2 of YR. And the
Positive is strict.
right, positive cone. Strict. And then the walls, this is locally polyhedral, and the walls of A of y bar correspond to curves of negative self-intersection. So there are three types. They're either interior exceptional curves. There are -2 curves, C. So C is smooth rational. And C intersect D is empty, and therefore C squared is -2. And then there are also the components of D. That'll be a wall if di squared is less than 0. Okay, so you can think of what the ample cone encodes, aside from the components of D, is what are all of the interior exceptional curves, what are all the -2 curves, and how do they meet? And in general, we'll say Y is generic if there are no -2 curves. And since that's given by a curve C, which has period point equal to 1, well, in particular, sorry, I should say. In particular, C satisfies this, and by the surjectivity of the period map, these are dense. Most pairs are generic. And in general, then you can ask what are the the interior exceptional curves on Y, which is the same as the walls of not equal to of the ample cone not equal to di in the generic case. And in general, this is a hard question. Okay, but one thing you can do is ask what's a numerical? So what's a numerical exceptional curve? And that's going to be an alpha with alpha squared equals -1, and then you could write as alpha dot ky equals -1, or equivalently, alpha dot d is equal to 1. And of course, more precisely, you know that you have to have alpha dot di equals 1 for exactly one I, and otherwise alpha dot dj is equal to 0 for j not equal to I. But this condition seems to be not, doesn't really come up as much in practice. And alpha is effective if, in addition, well, so here L alpha is the line bundle corresponding to alpha, but it's equivalent, essentially by Riemann-Roch, to saying that alpha dot h is positive, where h is the class of an ample divisor. And you could relax ample in various ways. And it turns out that for Y generic, this has walls pi and otherwise, well, I should say this. Well, it has to meet the components of di positively, and then it has to meet all of the effective numerical exceptional curves. And as a consequence, so this condition makes sense. This makes sense for any y, not necessarily generic. And I want to just define this to be, I'm just going to call it A bar, it's generic, the generic ample cone. Okay, and it's easy to show this is a deformation invariant. It equals the ample cone if and only if y is generic. So you can think in general what this is. It's you take a small generic deformation of y and you look at its ample cone. The main point is this is invariant. It's deformation invariant. In particular, it's invariant under monodromy. And maybe a sort of remark is, since this can be a cone in a kind of big space, you can show that this determines and is determined by its intersection with a potentially much smaller vector space. So this gives some sort of discrete deformation invariant. And again, something that's easy to see from the definitions. So let's call this a proposition. Two pairs YD and Y prime D prime are deformation equivalent. If and only if there exists an isometry, let's say gamma. So by this I mean an integral isometry preserving the intersection form, taking the classes of the di to prime to the class of the di, and taking the classes, taking this polyhedron to this one. Yeah, maybe. And that's not really very surprising because in the generic case, you don't have any -2 curves to worry about. You just have to worry about the -1 curves and how to blow them down. And that's really exactly the information that's recorded here. Okay. But maybe a more interesting result is the following. This can be used to classify the smooth topology. Of YD, okay, in a kind of weak sense. So let me call this a theorem. So suppose I have two pairs as above, then YD and Y prime D prime are diffeomorphic in the sense that, in the weak sense, there exists a diffeomorphism F from Y to I prime such that the classes of the di prime pull back to the classes of di, if and only if the pairs Y comma D and Y prime D prime are deformation equivalent. So in some sense, like K3 surfaces, this says that diffeomorphism of pairs is the same as deformation equivalence. Okay? And the idea of the proof is, well, this direction, this is fairly clear. If you have a deformation equivalence, you just use it to produce the diffeomorphism. And this one, well, it uses the proposition that I'm about to erase. So it's enough to show that F upper star takes the generic ample cone of Y prime to the generic ample cone of Y. Okay? And from this, you sort of do that in two steps. First of all, if T is irreducible, then you use a theorem of myself and John Morgan, which, well, you can use Donaldson theory or Seiberg-Witten theory, which essentially characterizes the possible diffeomorphisms between two rational surfaces. Okay? And then throwing in this condition, in the irreducible case, it sort of gives you what you want. And then in the reducible case, you reduce to the irreducible case. I should have used reduce here. By a smoothing argument using the result that I mentioned a little earlier. Okay. So sort of leads to the question if there's a more elementary proof, and I don't, well, maybe starting with a little less, but proving the same thing. And I don't really know. But well, it turns out this condition means it automatically preserves the positive cone. Well, you can check. Okay, so that in some sense is a sort of rough version of what are -1 curves in this case. And now what about -2 curves? So in some sense, we're asking the question that we could answer for del Pezzo surfaces if I'm given beta, well, in fact, beta in lambda, which is the orthogonal to the di, and beta squared equals -2. When can we deform so that when can we deform y so that beta becomes the class of a curve C, where C is isomorphic to P1 and C is disjoint from D. And there's a natural condition, namely if C is, so let me let delta y be the set of beta which are equal to C is above, satisfying these conditions. And that generates a Weyl group. So the group generated by reflections about such a thing, I'll just write as W of delta y. And then I can also apply the Weyl group to delta y. And I'm going to call this sort of following the set of nodal roots. Okay. Then, sorry? It's typically infinite. I mean, it could be. Of course, it could be finite, but typically it's infinite. Just the group generated by reflections. Okay, and then it's easy to see that if beta is equal to C and R beta is the corresponding reflection, then R beta of the generic ample cone is equal to the generic ample cone. So the reflections in these preserve the generic ample cone. And in fact, the ample cone itself is a fundamental domain for W of delta y acting on the generic ample cone. It could have, right, certainly could. If I mean, it depends on whether there are finitely many or infinitely many irreducible curves. Sorry? Well, I'm going to come to that. Okay, so, but in general, I'm going to find the set of roots if lambda is a root, or maybe a Luyenga root, if reflection under R beta sends the generic ample cone to itself. And then one has the following proposition. It's just the integral elements in H2 which are orthogonal to all components of D.
So beta here is a -2 plus.
Sorry. Yes. Roots should always have square minus 2. Okay. Proposition are equivalent. So first of all, beta is a root. Secondly, the wall perpendicular, a vector is perpendicular meets the interior of the generic apple cone. This is more or less automatic. The third one is on any deformation of y such that, say, y prime, such that p sub y prime of beta is equal to 1, then beta, well, it's almost the class of a minus 2 curve, but you have to put in some w here where w is an element of the Weyl group generated by the minus 2 curves. Okay. So in particular, there are strong conditions. Let me just maybe say an example. What's a typical example of a root? If E1 and E2 are two interior exceptional curves meeting the same component of D, then you can just look at the difference, and that's a root. Okay? And as we'll see in a minute, that's sort of a typical example of what a root is. For example, if you just deform these to the same curve, you'll pick up a smooth minus 2 curve here. But most, let's say, for blow-ups of P2 at least 11 points, most vectors of square minus 2 in lambda are not roots. In some sense, this was known to Duval, but Luliango really understood that and exploited it deeply. However, there's the following theorem. Right, but no. Most blobs P2 at 11 points on an irreducible nodal curve. Yeah, so even so, yeah, otherwise, of course, it wouldn't really be very interesting. So for most pairs that don't kind of fall in the purview of Del Pezzo or strictly negative semi-definite, the elliptic case, or something, I mean, as long as you get into the genuinely negative definite case, essentially, almost all the time, most vectors of square minus 2 are not roots.
The fact that the principal group is
Not arithmetic. That comes into play after, yeah. But anyway, one does have the following theorem. So let y be a pair. And let's assume that we're not in kind of the trivial case where y is f0 or f2, where you obviously have a root here, namely the negative section. And here, if you look at the difference of the two rulings, you'll also get a root. Okay. If beta is a root, then there, for any generic deformation of the pair yd, there exist disjoint exceptional curves E1 and E2 such that beta is the class of E1 minus E2. So in some sense, the only roots that there are ones that you might guess. But the proof of this is kind of long and tedious. I don't really know a simple proof. OK, so let me go back to the question I raised at the beginning, which is also what Rada was asking. So what does this say in terms of the symmetries? So let me define an isometry gamma from H2 of yz to H2 of yz is admissible if, first of all, takes the components of di to themselves, and secondly, it takes the generic ample cone to itself. Okay, and in particular, it'll take the positive cone to itself. So this is a deformation invariant definition, but I'll just put in a YD anyway, even though it only depends on the deformation equivalence class. This is the group of admissible isometries. Okay, so what are some obvious remarks? First of all, gamma is a subgroup of, let me call it O plus of lambda. These are the isometries from H2 of yz to H2 of yz. I want them, gamma, I want them to preserve the classes of the di. And the plus is just saying that it takes the positive cone to itself. Okay. So this is an arithmetic group. And gamma is naturally a subgroup of this group. And occasionally it can be the whole thing. And then inside of here, let me write this as W r sub y. Here, r sub y is the set of roots. And again, since these are vectors to square minus 2, this will generate a group by reflections. And by definition, this group is contained in this one. Okay? So what can you say? Let me just sort of conclude with a few things you can say. So first of all, this is due to Luenga. If r is less than or equal to 5, then in fact, these are the same. So this is sort of the analog of the Del Pezzo case. So you should think of gamma as the symmetries, the natural symmetries of the generic ample cone. They all come about by reflections. Sorry? Little r is the number of components. Okay. Secondly, there's certainly examples where the index of WR and gamma is infinite. So in the strictly negative semi-definite case, these are given by Gross, Hagen, and Kiel, but you can also give them in the negative definite case, which is the case that's interesting for singularities. Okay. And the last thing I want to mention, to give some sense of the size of gamma, so let's let E be the set of interior exceptional curves. then gamma acts, say, of a generic. Gamma acts as symmetries of the generic ample cone, and the walls are just these. So gamma will permute the set of interior exceptional curves, at least in the generic case. And then you can show, it's not really too hard, that a set of orbits is finite. And with a little more work, this says that gamma is infinite if and only if E is infinite. There's a similar statement for roots, but the implication here only goes in one way. OK, well, let me stop here and see if there are any questions.